Now we're going to finish up with section 8.2, and just as a little review, remember we were looking at experiment 2 where we were rolling a die and looking at a success being a 5 or a 6 coming up. And once we got that 5 or 6, basically we were stopping. So we were counting and letting x stand for the random variable of how many times it takes to roll to finally get that 5 or 6. Now, I could grab a die, but instead of grabbing a die and making that noise on the video, I'm going to actually perform this experiment with a little random integer feature. So let's see how many times it takes me to roll and get my first 5 or 6. So I'm going to roll the die. Oh, I got it on my first time. Okay, I'll clear that entry out. Okay, let's play again. I'm going to roll again. I got a 1. I got a 6. Oh, took me 2 times. Clear that out. Let me roll my die again. I got a 1. I got a 1. I got a 6. Took me 3 times. Clear that out. I'd be kind of freaked out if this is going to be a 4, but I'm going to roll my die. Whoop, got it on my first time. Now, if I continue to do that over and over again, I'm going to roll. 1, 5, took me 2 times. I would continue to do this over and over again and look at what type of occurrences happen here. And we know I haven't done very many trials. I've only done 5 trials, but we know in reality that a third of the time I would be done after 1 roll. We know 2/9 of the times I would be done after 2 rolls, and so on. And it could be that I have to sit there and roll that die many, many, many times before I finally get a 5 or a 6. However, it's not likely it's going to take me far beyond 5. Now, I can see that if we turn the page and we look at something called the cumulative frequency distribution. So a cumulative frequency distribution would be if I'm looking at what's the likelihood that it takes me 1 or fewer times, 2 or fewer times to finally get that 5 or 6 coming up. And so we know that this event, say right here, would be the event that it happens on the first or the second or the third final roll that you finally get that 5 or 6 coming up. So this is really 3 of my probabilities from the previous chart, the probability of x being 1, 2, and 3, to accumulate to be this value. And we do have this nice little feature on the calculator that is a geometric CDF, and that's located, once again, under the distribution button. And if I arrow up rather than down, this cumulative frequency button, I use that by entering in the probability of finally getting that success. And in our case, the 1 divided by 3 stood for either rolling a 5 or a 6. And if I wanted to know what is the probability that it will take less than or equal to, say, 10 times to finally get that success, and I have a 98% 3 chance of having it happen in 10 or fewer rolls. So this is a nice feature that it accumulates. Now, I'm not going to cover letter D. We've already talked about that in the past, so you can look over that. That's the information for it. If you want to look at it, stop the video, and you can look at what I have written there, and then you can ask about it in class if you have a question. But I want to look at, we just talked about this button, and I want to look at a couple little features that we have. So we know that the geometric CDF, just like we have a binomial CDF, accumulates the probability of our situation taking x or fewer times to finally reach that success. And when I was rolling my die before, and remember it took me 1 time, 2 times, 3 times, and so on, to finally get that 5 or 6 to come up, these numbers were not all the same. I had, again, with my very few trials, I had 1, 2, 3, 1, 2, and it could take me several times to finally have a 5 or 6 to come up. But the context of what it means to find the expected value or mean is if I do that, performing that experiment over and over and over again and count how many times it takes me to finally get that 5 or 6, the mean of that random variable, or the expected value of that random variable for a geometric setting, is actually very easy to find. It's 1 divided by the probability of a success, which really means this is the reciprocal of the probability of a success. standard deviation of these values, so again, back to this little piece of paper, these are not all the same values, so we know that they do vary. And the standard deviation of these values, theoretically, will come out to be the square root of 1 minus p, p being the probability of finally getting that success, over the probability of a success, which means this is really the probability of the square root of a failure, because 1 minus p is really the probability that you fail, divided by the probability of what that final success is. We're not going to prove that, but that is what this variability would end up being for that geometric situation. Now, there's another really nice feature on geometric probability that we don't have with binomial probability. And remember the context on binomial probability. If I, say, rolled a die a specific number of times, say I rolled a die 15 times, and I let the probability of the die coming up a 6 be my success. So I would have a 1/6 chance of having a 6 come up. And if I said to you, what's the probability that I will have less than or equal to, in 15 rolls, less than or equal to 5 6s? Well, that would be the binomial setting, because I'm rolling the die a fixed number of times, as opposed to a geometric setting would be continue to roll the die until you finally get a 6. So in this case, I don't have a shortcut. I know I can write my sigma notation to calculate this out. I can say I know that the probability of a success of rolling a 6 is 1/6, and I know the probability of a failure is 5/6, and I know that I'm going to have a specific number of successes, and I know that number can be 5 and fewer, and the number of alternative values of failures are going to be 15 minus I. And then there's going to be a combination here, because we don't have to have specifically the first numbers be the 6s and then the last numbers be the non-6s. We can have them all mixed up, and that combination checks that for us. And so if I let this go from having no 6s all the way up to 5, this allows us to find the probability of a whole bunch of events. Now, writing in that notation doesn't make it easy to find. We really like to have this button. If we have the geometric, and getting out of the glare, if I have the binomial CDF button, I can plop that in and have the 15, 1/6, 5, and that will accumulate and add all those probabilities up for us. Now, we don't have any other fast way of doing that unless we have that button. If we don't have that button on our calculator, we're kind of caught where we'd have to figure out a whole bunch of probabilities on our own. Now, that's not the case for geometric. Geometric has actually kind of a cool case, and we have a way with geometric of actually adding up a whole bunch of events, in fact, infinitely many events, with this formula. And again, we're not going to prove it, but we'll look at what it means. Let's say in a setting that I wanted to know, we're in that situation where a 5 or a 6 is our success. And let's say I ask you, what's the likelihood that it's going to take you more than like 5 rolls to finally get that 5 or 6? So it's going to take 6 rolls, or 7 rolls, or 8 rolls, or 9 rolls, or 10 rolls, etc., to finally get that success. Now, there are infinitely many things to add up here, so we know we can't straightforward do the calculation of this and this and this. Now, we can figure this one out individually and go, well, we want to get non-6s. We would have 5 rolls, and this is supposed to be 1/3 or 2/3. I'm kind of messing up here because we're getting a 5 or a 6 as a success. So we would have 5 non-5 or 6s, and then we'd finally get that 5 or 6, and then we'd have to find this one, and the next one, and the next one. And we definitely, if we were going to find this by a straight format, we'd actually have to go through and find the complement. We'd have to find all those things that we don't want, and then take 1 minus to find what we do. But Geometric has a cool feature, as I said before, that we can actually answer this question in a geometric setting by taking 1 minus the probability of a success, and our success is rolling a 5 or a 6, which is 1/3, and take it to that power. So if we take 2/3 to the 5th power, it actually adds all of these things up for us. And it would give us the same answer as if we actually went through and found all of those that are below the 1, 2, 3, 4, 5 events, because remember, we can't have a geometric setting have the variable be 0, because we have to have one success. We have to have one roll. So this would be finding all of the 1, 2, 3, 4, and 5 events and doing 1 minus, but this calculation finds us, boom, directly. So kind of a neat feature. Now, let's look at the next page and we'll finish up these examples and then you'll be ready to practice. So we have a setting that we have a basketball player and she makes 70% of her free throws. And we put her on the free throw line and we ask her to shoot until she misses. And then we count the number of free throws that it takes for her to miss. So this is going to end up being the geometric setting as long as we have independence between shots. And we have, again, she's either going to make or miss. And we're going to have her continue to make shots until she misses. Now, what would be the probability that this player will make 5 shots before she finally misses? Well, that means she's going to have 6 shots. She's going to make her first 5, and then boom, she finally misses that last shot. What's the probability that she will make at most 5 shots before she misses? So at most 5 shots before she misses, and think what that means. At most means she can't make any more than 5, but she could make less than 5 before she misses. So it could be maybe she only makes 3 and then misses. So, but it's at most 5 shots. And this really equates to this idea in the geometric setting, that we're looking at the total number of shots that she'll have is going to be 6 or fewer. So the most she would ever have is 5 made shots and then followed by that last one being missed. Now this is accumulatively. Could be she misses the first shot. Could be she misses the second shot, or the third, or the fourth, or the fifth, or the sixth. And if we add all those up, that would come out to the correct probability. Now, we actually can find something that we don't want. Because remember, the geometric setting allows you to accumulate upward very easily. So we want 1, if we think of the probability distribution for the geometric setting, we want 1, 2, 3, 4, 5, and 6 to count. We don't want all of these that are up this way, which again, we know there are infinitely many numbers that are up this way because the geometric setting never ends this way. And recognize that if we find the probability that x is greater than 6, which means 7, 8, 9, etc., if we find that probability, this stuff is the complement of actually what we want. So we really can take and find this probability with the probability of a failure to the 6th power, and that finds the probability of all of these events up here, and if I take 1 minus, I'll get this probability. So here was one way of setting it up where we actually find the individual probabilities here. A second way is to utilize that formula that anytime in the geometric setting that you want greater than some number of times, that I take the probability of a failure to the nth power. And so we could utilize that. Now we can also write down this type of probability in a sigma notation rather than writing all these events out, because we know that you can use the geometric CDF in order to calculate those. The geometric CDF If I type in the probability of finally getting the miss, 0.3, and type in 6, that will actually find all of these probabilities. But remember, on the AP exam and on our exams, this is not the appropriate way to write out your work. You'd either have to write this out or look at the trend of what happens here. We can do this a couple different ways to write the sigma notation. I have one way down, and I can jot down another way too. That if we write down each time in our sigma notation, we know we have 1, 2, 3, 4, 5, 6 terms. So we could say every single one of those terms has a 0.3. I'll kind of put that at the end. And then all of them but this first one has a 0.7. And we know that we're multiplying a whole bunch of 0.3s times 0.7 to the power of how many times we basically missed or didn't have the success, and then finally got this one. Now, a few different ways to write this out. I can write this like so and then say, okay, this first time, I know I need the 0.7 to be to the 0th power because I don't want it to appear. So I can let I equal 0, and then I'm going to want it to up to 1, to 2, to 3, to 4, and then to 5. And so this will actually help me find all of these probabilities instead of writing the whole kit caboodle out, just to write it down in a sigma notation, and this means all of this. And if we do that calculation again, we'll end up getting the 0.882. Okay. Now, you could also go through and write something like this that looks more in line with the formula, and you could say, I'm going to let 0.7 be to the I minus 1. And then you would start the counter actually out with, did it happen on the first time? And if I put 1 in there, this would be 0, and this is automatically going to be a 0.3. And then you would go up to this being consistent with this number, going up to the random variable being 6. And notice that if I put 6 in here, I'm going to again be at this 5 that I need. So we have a couple different sigma notations that can be used. It can be written out longhand. It can be written out utilizing that idea that geometric has that great setting that you can actually accumulate upward with that formula. Now let's finish up with letter D. What is the probability that she makes 3 of her first 6 shots? 3 of her first 6 shots. Well, now I'm actually changing gears. I'm having her shoot 6, specifically 6 shots, and I'm not dealing with shooting until she misses. So I'm having her do something differently. So I'm dealing with now a binomial setting. She will have 6 shots, and she's going to miss 3 of them, but I don't know which 3 she's going to miss. So I can think, well, here's her making 3, here's her missing 3. If she's going to make 3 of her first 6 shots, it means she has to miss 3 and make 3. And our combination is going to be all the different ways of having her in different orders have those shots. It could be she makes the first 3, misses the last 3, or vice versa, or makes the first 2 and makes the last 1, and so on. And that combination of 6, choose 3 is going to tell me all those different ways that happens. Now, it's fine to use binomial PDF and put in 6, comma, 0.7, comma, and then 3, but you definitely need to write out this type of notation. You can use the C there. On the average, how many shots will it take her to finally miss a shot? That's asking you to find the expected value for a geometric setting. And so we know that that's 1 over the probability of, and we're to finally miss a shot, 1 over the probability of success, and a miss was actually a success here. And so it would be 3 1/3 shots. And the standard deviation for that setting, there's our setup, utilizing the formula from the previous page. And now you're ready to practice.